Hello, so today we are going to discuss what are simplexes. And to define the simplexes, first we should know what are affine subsets. So, affine subset is a set in which for any 2 points, if there is a line joining them, must be in that subset. For example, R2 itself, lines, and singletons. Convex subsets are the subsets in which the line segment joining by 2 points is again in that subset. Now let us define what is affine independent. So consider P is a set of points coming, then the difference of each point from the point P naught will form some vectors. And if the set of these vectors are linearly independent, then we call it as affine independent. For example, consider this set of points coming from R3, then these V1, V2 are the vectors that are formed by the difference, and V2 is linearly independent to V1, so we are good in this scenario. Hence, P is an affine independent set. Now moving towards affine combination, it is similar as a linear combination of points, but with an extra condition, as you can see, that the summation of all the coefficients should be equals to 1. So for example, consider points from R2 like P0 and P1, then if their summation is equals to 1, then we have such equation T0 plus T1 equals to 1, and this implies that I can write my T1 as 1 minus T0, which provides an equation of a line. So X lie on this line. This combination shows us this geometrically. So now what is convex combination? It is something similar, but with an extra condition that our all the coefficients are positive. Then our combination is known as convex combination. So what happens if our all the coefficients are positive? So consider the same example as previous. Then if all the coefficients are positive, then it means that T naught and T1 cannot be negative. So this means that our T naught will not going to be more than 1, and it is also not going to be less than 0, because either case either T naught will become negative or T1 will become negative. So this implies that our line is restricted to our first quadrant. So it actually becomes the convex combination, as it restricts our line to a line segment in the first quadrant. Next, now we are able to define what is a simplex. So consider points P, set of points coming from Rn, and these points are affine independent, and a convex set that is spanned by these points that we denote as square brackets is known as n simplex. For n points we call it n simplex. So the main crux of this definition is the convex set that is spanned is actually the collection of all convex combinations, right? So it is the simple definition of what is span means in linear algebra. So these are called simplexes. Now let us consider some of the simple examples of simplexes. So considering if we consider one single point, and a single point is an actually affine independent, because we know that if I take a single point P naught, then P naught minus P naught will be empty set or phi. But we know that phi is actually a linearly independent set, hence we can conclude that P naught is actually an affine independent set, and the convex set that is spanned by P naught is actually a single point P naught itself. Here I have one point, so my simplex will be called zero simplex, and just to make a representation of geometrical perspective, consider this point as a zero simplex. Similarly, if we increase the dimension of points, like consider 2 points, p naught and p1, it is again known as a one simplex, and it is actually a set that we have already discussed, because the convex set spanned by these 2 points will look like this, and it is actually the closed line segments with the endpoints p0, p1. This is because the condition of that t's should be greater than or equals to 0, since we are dealing with the convex combination. So it is just the matter of recalling the convex combination definition again. So you will end up with the this type of line. So this is the example of one simplex that has been generated by p0, p1, and they are affine independent if they are not equal. So we have taken p0 not equal to p1, so they are obviously affine independent. So now consider our example of two simplex in which we have 3 points which are not actually collinear. So if I make a vector by making a p1 minus p0 and p2 minus p0, then I will get two vectors that are actually linearly independent, since we can see by geometry here, since they are at 90 degree. Such collection of points are actually affine independent. So first condition holds, and for the second condition we have to check what kind of convex set is spanned by these 3 points. So actually, if try to write first a convex combination, so it should be all those points x that are represented in terms of p0, p1, and p2, such as these points where the summation of the coefficients should be equals to 1, a condition coming from the affine combination, and these all t's must be greater than equals to 0. So consider t not equals to 0, then again it becomes a case of one line that starts from p naught and ends at p2, and if I take t1 to 0, then it will again make the same case of that we have discussed in the one simplex case. So it represents a line that starts from p naught and end at p2. Similarly, if t2 equals to 0, then it should be a line starting from t naught up to t1, right? So the case will be these three lines. But when I take all the components greater than 0, then you are going to end up some point here, interior to the triangle. And similarly, if I take the whole linear combination and take the set of all these elements x that are represented like this, such that my all the ti's are actually greater than equals to 0, then the points are in interior and or inside these three one simplexes on the boundary. So the convex combination spans a set that is actually the triangle that is not hollow, right? So we have triangle with an interior as an example of two simplex. Similarly, if I take 4 points, then I am the three simplex will be a tetrahedron, and if I increase my number of points, then I am going to end up with polyhedrons. So the simplexes are actually geometrically the polyhedrons. So this was the simple introduction of simplexes, and we have also seen their geometrical interpretation as well.